Welcome everyone, and thank you for joining us today. My name is Kalliroi Stavrianou, and on behalf of Global Clinical Engineering Alliance, I'm very happy to moderate this series of webinars that aim to educate, promote collaboration, and also promote information exchange about healthcare technology, engineering, and patients' outcomes. All our webinars are recorded, archived, and also live streamed on Facebook. Following the completion of the webinar, the recording material will be accessible on our website, www.globalceea.org. Please note that at the bottom of the screen, you have a Q&A button where you can submit questions to the faculty, and those questions will be addressed towards the end of the webinar. In addition, for posting general comments, there is the option of the chat box for audience interaction. Please use only the Q&A for your questions and not the chat box. Today, GCEA is really excited to announce the addition of the new live translation feature that we believe will bridge the language gap and enhance your video conference experience through Global Clinical Engineering Alliance programs even further. As part of our commitment to delivering innovative and educational video communications training, we have incorporated a new captioning option that facilitates the ability of our members to elevate their understanding of the spoken content during GCEA education and meeting events by simultaneously customizing captions in their preferred language. All you have to do is simply click on the Captions tab at the bottom of your screen and select the caption language you would like to read from the drop-down menu. And now, I would like to introduce today's webinar, which is the fourth in the series of imaging equipment, and today focuses on PET scanner, positron emission tomography. And now I'm very pleased to give the floor to the webinar's moderator, Nicholas Palikarakis, who is Emeritus Professor of the University of Patras in Greece, GCEA's Founder Council member, and Chairman of the Institute of Biomedical Technology, INBIT. Nicholas, I'm very pleased to give you the floor.
Thank you very much, Kalliroi. I'm also excited to moderate one webinar in the series of the webinars of GCEA, and I would like to thank Professor Khalil for inviting me to be moderator in this important event. Actually, I'm excited also because in the 80s, I had the chance to work with a PET installation, and we were at that time studying glucose metabolism using carbon-11 glucose. But I will not take more time on what I did with PET because we have three very eminent speakers to speak about. The first one will speak about the basics of PET principles, and the second on safety in PET, and the third one about the implementation of service programs and follow-up of the technology, which is very complicated. Before starting and giving the floor to the first speaker, I would like to ask Kalliroi for the first poll questions that will provide us with some information about you. So please respond to this poll. The first question is, do you have a PET scanner in your facility? And the second, do you anticipate being involved with PET scanner maintenance? So please give your answers within the next 20 seconds, please. Most of you have not a PET scanner in your facility, and also you don't plan to be involved in PET scanner maintenance. Okay, thank you very much. So we are going to start this webinar. The first speaker is Dr. Edna Marina de Souza. She is medical physicist at the Biomedical Engineering Center at the State University of Campinas, UNICAMP. She graduated in medical physics and then continued with her master's degree and PhD in biomedical engineering at the same university. Now she teaches nuclear medicine at the Medical Science School of UNICAMP. Her activities include nuclear medicine and magnetic resonance physics and instrumentation, and she's working and teaching, and her research is related to the corresponding areas of medical physics and biomedical engineering. She's also an ad hoc reviewer in the Brazilian Department of Health projects and a reviewer of scientific journals. Edna, the floor is yours. You can start.
Thank you, Professor Nicholas, for the introduction. Hello, everyone. It's a pleasure to be here today. First of all, I would like to thank the Global Clinical Engineering Alliance for the invitation and the Professor Khalil. Next, please. Here we have a night view of our university, just for illustration, right, from UNICAMP. Next, please. First of all, let me give you a brief concept about nuclear medicine. Nuclear medicine is a medicine area that applies radioactive materials linked to pharmaceuticals for diagnosis and therapeutical purposes. Diagnosis is basically related to detection of the metabolic activity of the tissues using machines and techniques such as PET or scintillator camera, for example. And therapy applies specific radiopharmaceuticals to treat many kinds of diseases. Here in the middle, we have an illustration of a radionuclide connected to the pharmaceutical, creating what we call a radiopharmaceutical or radiotracer. When injected into the body, the radiopharmaceutical is going to be uptaken by the organs or tissues that applies it in their metabolic activities. Then the radioactive emission from radionuclides can be detected by imaging scanners to create a metabolic image of the body, as you can see on the right, highlighting the main points of uptake of the radiotracer. Next, please. If you search the word PET on the web, that's what we see, basically. A lot of dogs, cats, pigs, even bottles, and despite being cute, it's not what we are looking for right now. We are trying to find something about medical imaging techniques, right? Next, please. So what is PET? PET means positron emission tomography. On the left, we have an example of a PET scanner, PET machine. It's a metabolic imaging technique based on insertion of a radiopharmaceutical positron emitter in the patient's body. When the case, the radionuclide releases a positron, a nuclear particle, which match an electron of the medium, and both suffers a process called annihilation, from which we have, as a result, two gamma rays released in opposite directions and detected by the scanner, as I'm going to show you on our next slides. In the example on the right, we have an image based on the radiotracer called FDG, which is a glucose-like molecule labeled with the positron emitter fluorine 18. So all the tissues with high glucose activity tend to uptake most of the FDG injected, and the image displays the biodistribution of this molecule across the body, as you can see in the image on the right. Next, please. So considering that tumors in general have a higher glycolytic activity when compared to normal tissues, the FDG is increasing for detection and follow-up of a lot of tumors and many types of lesions, right? Here we can see some examples of sarcoma, melanoma, cancer colon, and in these images, we have the contrast in inverted grayscale, where the regions of higher FDG uptake are darker. So we can see the lesions darker, the brain darker, because we have a high uptake of FDG in brain in normal conditions. Next, please. Another radiopharmaceutical used for tumor detection and its therapy follow-up is the gallium-68 DOTA-TOC, used in case of neuroendocrine tumors. On the left, we have the PET image of a patient with multiple lesions from neuroendocrine cancer, and B and C present the PET images after 1 and 2 cycles of therapy using actinium-225 DOTA-TOC, other kind of radiopharmaceutical. You can see that the same molecule, in case DOTA-TOC, is used for images and for therapy. The difference is the radionuclide, being the gallium-68, a positron emitter for diagnosis, and the actinium-225, an alpha emitter, interesting just for therapy, right? But our focus here is just images. Next, please. So here we have some other applications of FDG in case of unknown orange fever, which can have many causes, such as bacterial infection, autoimmune encephalitis, osteomyelitis, and others. Next, please. And here, one more use of FDG in arteritis, and brain images of carbon-11 Pittsburgh compound B of a patient with Alzheimer's disease, and a lung study of a patient with pulmonary embolism using a gas containing gallium-68. Next, please. So, as a complex medical imaging technique, PET is the result of much knowledge generated over time. Among them, we can mention the discovery of natural and artificial radioactivity, the development of cyclotrons and radionuclide generators, which are the main sources of radionuclides used in PET. Next, please. And finally, we have the project and development of the PET scanner. The first report of PET system dates from 50s, when Bromwell and Sweet described a multi-detector system to acquire coincidence images from positron emitters. The system was applied for the first time to detect the metabolic activity of brain tumors, as we can see on the right. Next, please. After that, Yamamoto proposed an upgrade in the Bromwell's system, increasing the number of detectors and also changing the acquisition setup. In this case, he put the patient sitting on the chair for the scanner. And on the right, we have an example of the images acquired. Next, please. And here we are. Finally, we have examples of the modern PET scanners as we know nowadays. The first one was proposed by Phelps and Hoffman in 1973, right? And on the right, we have the modern machines that we have. Next, please. So before to explain how the images are acquired, I'm going to show you some examples of the main radionuclides used in PET exams. Most of these radionuclides are produced in cyclotrons, which are particle accelerators and generators that are commonly found in nuclear medicine facilities. So some of the radionuclides that we have are fluorine 18, that is the most applied, followed by gallium 68 and others. Next, please. And here we have some examples of radiopharmaceuticals and their applications. FDG has a lot of applications in tumor detection and staging, inflammation and infection, cardiovascular diseases. We also have some applications of gallium 68 and other radiopharmaceuticals. Next, please. So finally, let me guide you through the arrows to explain how the PET image is acquired, considering the example of the FDG radio tracer, right? First of all, the FDG is injected into the patient's bloodstream, as you can see here. Then the patient remains at rest for 1 hour before acquiring the images. This time is the biodistribution time of the radio tracer, when this accumulates in the body tissues with a high energy demand, a high glucose demand, which occurs especially in tumors, right? Next, please. The FDG moves from the blood vessels into surrounding tumor cells. Then the radioactive decay of the fluorine 18 inside the tissues releases nuclear particles called positrons. These positrons react with nearby electrons in an annihilation process, producing a pair of gamma rays in opposite directions. Finally, next, please. Sorry. Finally, pairs of the gamma rays are detected by the scintillator crystals present in the scanner. Thousands of detectors to capture the gamma rays in coincidence and decode the information, creating then a metabolic image of the body. In case of FDG, a glucose metabolic image, as we can see on the last figure, right? So what about the signal detection? Let me give you some aspects of it. When the annihilation process occurs and 2 gamma rays are released, a line of response is defined, as we can see in the first and in the last figure on the slide. Only the gamma rays detected in coincidence will be included in the image. And to be considered a coincidence, the difference between arrival time of gammas to the opposite detectors in the gantry must be about 6 to 15 nanoseconds, for example, just to give you an example of a time range to consider a temporal coincidence. The definition of the time of flight of the gamma rays before reach the detectors can contribute to spatial resolution of the images. And the line of the responses defined by the gamma rays are combined using reconstruction techniques to create a metabolic image of the body. Next, please. So in this figure, in the middle, we have an example of PET gantry without its cover, where we can see a lot of detector blocks positioned in the gantry. And on the right, we have blocks of detectors showed, where we have, in this case, 4 photomultipliers linked to the crystal blocks. And then when the gamma rays from the annihilation process reach the crystal, the radiation energy is converted into visible light in a process called scintillation. Then the visible light is guided to photomultipliers, where the light is converted in electrical signal, which is also amplified in this device to follow then the processing sequence until we have the image, right? So a typical PET scanner has nowadays thousands of scintillator crystals organized in blocks, as you can have here, right? Next, please. So here we have a view of 2 types of scintillator block detectors that we can find in PET scanners today. They are the BGO and LSO. So here we have these examples to give you an idea of the size of these blocks and the detectors, right? Small detectors contribute to increase the spatial resolution of the images. However, we have to remember that spatial resolution does not depend only on the size of the detector, but also on the other factors. Next, please. And finally, here we have some examples of hybrid methods involving PET that are PET-CT and PET-MRI. In this case, the images were acquired in hybrid machines, a CT or MRI plus PET scanner in the same machine, right? In both cases, we have the combination of the metabolic information from PET and the anatomical information from CT or MRI, allowing the anatomical positioning of the activity detected by PET technique. Furthermore, we have the CT data used to create an attenuation correction map, which may correct some effects of the body patient's attenuation on gamma rays that leave the body towards the PET scanner. The use of MRI for attenuation correction is a little bit more complex because MRI is based on different physical principles, but it's also possible. And MRI has a lot of advantages, such as higher contrast for soft tissues. So to investigate, to explore the lesions in different ways, it's a great technique, right? Next, please. Thank you very much for your attention. Now we will have some questions to the audience, and I'm here for any questions that you have.
Thank you very much, Dr. De Souza. While you fill in the quiz, I would like to thank very much Dr. De Souza for this excellent presentation of such a complex technology in just 20 minutes. It's really
difficult.
a challenge to do so, and thank you very much for the presentation. So next is safety in pet. Safety is very important in pet because apart from the fact that we have very complex technology, is also radioactive biomolecules that are used. And this is the subject that will be presented by Dr. Jacobs Claire, who is clinical scientist working in nuclear medicine at NHS in Nottingham. She's qualified and provide for 15 years and provide physics support to the PET center at Nottingham. And she's also an advisor for radioactive waste material. So Claire, the floor is yours. Thank you very much for being with us.
Thank you very much for the introduction. I'm just going to share my screen now. Okay. Can you see my screen?
Yes, but you have to move to the first slide. Fine. Okay,
great. Thank you. Okay, so thank you very much for the introduction. Yes, I'm going to talk about safety in PET, in particular the radiation safety. So first of all, a risk assessment is used to identify the hazards and engineering controls that we need in order to perform the work safely. So listed here are items that we need to identify in the risk assessment. So first of all, we have to identify the hazards, think about what engineering controls, design features and warning devices we need. Also provide a system of work to restrict the radiation exposure, and also provide personal protective equipment. So in terms of the radiation, there are 4 different sources of radiation that people can be exposed to. First of all, you've got the X-ray emissions from the CT part of the scanner. You've also got radiation emitted from the patient who's been injected with radioactive material. You've got the vial, the stock vial from which the radiation from which the patient doses are dispensed, and that contains quite a lot of activity in the order of gigabecquerels. And then finally, you've got sealed sources in the form of QA sources that are used to do image quality checks on the scanner. So these are long-lived, sealed radioactive sources, solid sources. So in terms of the effects of radiation, there's 2 categories of radiation effects. So firstly, you've got deterministic effects, which occur above a threshold radiation dose, and they tend to be higher radiation dose thresholds, and the severity of them increases with the increased doses. An example of this is radiation-induced cataracts, acute radiation sickness syndrome, and erythema, so reddening of the skin. In terms of PET, it is possible for staff to receive high skin doses if handling syringes and vials containing activity without the use of proper shielding. So it could result in thresholds where skin erythema could occur. The second category is stochastic effects, and for this we assume a linear no threshold model where the probability of the effect increases linearly with the radiation dose received. And we assume no safe lower limit, and this is the basis for all of our radiation protection. Examples of effects include cancer induction and hereditary effects. So next we have to identify who might be harmed and how. So people who might be exposed to the radiation are staff working in the department. You've also got members of the public in and outside the building potentially. You've got contractors who may come on site to do some work, and you may also have visitors. In addition to external radiation doses, you have to think about you're dealing with radioactive liquids, so there's a potential for contamination which could get onto skin and potentially be ingested. So what type of radiation are we dealing with? So as Edna mentioned, we've got gamma ray emissions from a positron emission, a positron emitter. So the most commonly used PET tracer is fluorine-18, and what happens is a proton in the nucleus is transformed to a neutron and a positively charged electron called a positron. This positron is emitted from the nucleus and travels a short distance of 1 or 2 millimeters before finding an electron in the patient's tissue. And the electron and the positron annihilate to produce 2 gamma rays of 511 kiloelectron volts in opposite directions. So they're very high energy gamma rays. If we compare this to the CT scanner, so that the top image on the right is an image of a CT tube where you've got the cathode, heated cathode, which accelerates electrons across a potential difference. And the X-ray spectrum produced is shown in the bottom left. It's called a Bremsstrahlung spectrum with the maximum photon energy be equivalent to the tube voltage. And but you can see that most of the X-rays emitted are actually much lower than the maximum X-ray energy possible. So on average, it's between 1/3 and 1/2 of the maximum X-ray energy, which is typically somewhere around 40 to 50 kiloelectron volts. So the energy from the X-ray tube, the X-ray energy is much lower than the gamma rays from the radiopharmaceutical injection. So lowering radiation dose in practice, we can consider different aspects. Firstly, we can consider time, minimising the time in proximity to the radioactive source, maximising the distance, using shielding between the source and the person, containment, because we're dealing with radioactive liquids, and good housekeeping, so minimising the amount of clutter. So if we consider shielding, when we're designing a facility, consideration needs to be given to the shielding required in the walls and possibly the ceiling to minimise radiation doses to staff and also to members of the public who might be outside the building. So here are some pictures from a new facility at Nottingham where there was engineering brickwork was used to create new walls in a PET facility. So it's high density brick to create new walls, and then on existing walls there was layers of lead applied to existing walls to create additional shielding. The aim being to have about 1 centimetre lead equivalents in the walls. So at the photon energies of 511 keV, it reduces the dose rate by about approximately 1/4. In terms of engineering controls, this is a picture from a laboratory where the radiopharmaceutical is prepared. So you have lead-lined cupboards, so typically a few centimetres thick lead in the doors and the cupboards. You've also got a body shield here and a lead glass screen so that the operator can see through the lead glass and look at what they're doing, how they're handling the radioactive material. Here's some more pictures of equipment that they use. So the syringe shields, which go on the outside of the conventional syringes, plastic syringes. They're usually made of tungsten or lead with a small lead glass window here so that you can see what volume of liquid you're drawing up. You've also got the body shield with the lead glass window here. It's 5 centimetres thick or so of lead glass. And then this device at the back here is, again, it's a lead lined container to put the vial in, the vial of the radioactive material, and then the operator will insert the syringe into this holder here. And then once you've dispensed it, you need to transport it to the uptake room where the patient is. And to do that, you use a lead lined case and a transport trolley. And in some centres, they have an automatic PET injector cart. So this does the whole thing for you in that it dispenses the dose and also injects it into the patient. So it's to try to minimise the radiation dose to staff. So going back to the principles of radiation protection, in terms of time, the dose received is proportional to the time that we're in proximity to it. So you only need to be in the vicinity, make sure you're only in the vicinity of the exposure for as long as you need to be there. In terms of distance, if we assume a point source of radiation, doubling your distance will result in 1/4 of the radiation flux intensity for the same area. So the radiation dose rate drops off quite significantly with distance. So that's important when considering keeping your distance from a patient when setting up for a scan, for example. In terms of the facility, we use things like warning signs and warning lights. So the example on the left is a radiation warning sign to indicate the hazards present. So we've got unsealed radionuclides, so liquid sources, there's a risk of contamination. On the right hand side, this is the typical illuminated sign used for outside the PET scanner room, and the do not enter sign lights up when the CT is being exposed. Containment, because we're dealing with radioactive liquids, is important. So the central image here is a picture of something we call a drip tray. We've got absorbent material on it, and this is to catch any radioactive spills, so it's contained. Got to ensure that your work area is clutter-free as much as possible, so if you do have a spill, it's easy to decontaminate. And also we consider this in the design of the facility, and bottom right you can see some laminated flooring in the controlled area, which is a continuous floor, so you reduce the amount of gaps and interfaces where contamination could be difficult to reach. In the UK, we have to have things called local rules, which are written procedures identifying the main working instructions intended to restrict any exposure in controlled and supervised areas. So they should include steps needed to control the exposure in the event of a radiation accident. And the most likely accident is a spillage of radioactive material. So we have to have things like a spill kit, which is a pre-prepared box or kit with all the things in that we need to decontaminate if there was a spill. And operators usually use, on a routine basis anyway, disposable gloves and disposable whole body suits. Because we're dealing with radioactive liquids, we need to monitor the areas for contamination. So we have a variety of these available. We have the portable ones on the left and the hand and foot monitors on the right. So the hand and foot monitors are less portable, but they tend to be positioned at the exits and entrances of radiation controlled areas. Staff are monitored, so they're monitored to ensure that they are receiving doses lower than the regulatory limits. So we typically wear a whole body badge typically at chest level or waist. Finger rings as well are used, and finger stoles are particularly worn if you want to look at the dose to the fingertips. Often what's also used are electronic personal dosimeters, which give you a real-time update of the dose being received in terms of your whole body dose and your skin dose. Thank you very much for listening.
We thank you very much, Claire, for this so well structured and presented talk on the origin and principles of radiation protection in PET imaging facility. Really, it was great the way you presented it, the simple way you presented so complex issues, and we thank you very much for this. Can we have now another quiz or not?
Not yet. It's during the presentation of Giulio.
Oh, okay, okay. Then we move to the third presentation concerning the way that this very complex technology is organized, the technology service and maintenance and corrective preventive maintenance and so on, that will be presented by Giulio Iacchetti, who is Manager of Health and Technology and Innovation at Medipass. Medipass is a service provider for said cities, centers and cyclotron units in Italy. Dr. Iacchetti has 9 years of experience as project manager during programs for PET CT scanners and radiopharma production unit. And he's manager of several other related projects in installation of diagnostic devices. So I would like to give you the floor now, Giulio, please.
Thank you, Nicholas. It's a pleasure to be here. I want to thank the Global Clinical Engineering Alliance. I would just start my little speech giving you just some insight on partnership service model that I think that are very related to this kind of complex department. Generally, like clinical engineering, we are focused on technology, organization, and professional. We always have to think when we speak about nuclear medicine department in general, that is I think that is the most difficult diagnostic imaging department to think of because of task action, information flow, and quality. So it's very important to have the right flow and the coherence of each phase that is strongly interrelated from the feasibility analysis to the clinical management. So it's very important to have, I think, in some cases, a partner where the project is a very complex one. But let me go on the focus on my speech. I would just show you, first of all, I would say that the general flow, workflow of the patient, considering a typical layout of a PET-CT department. This is the PET-CT department of Gemelli Hospital in Rome. You can consider, in general, you have always to consider different areas. We call cold area, hot area is not a dependency on temperature, but if it's possible to have people who are, I would say, lightly radioactive are injected in the cold area. You don't have anyone of this kind of people. In the second one, you have patient And in general, you have different activities that you can do in cold area and in hot area, and different kind of safety action that are permitted. The flow of the patient, in general, you have, as in each diagnostic imaging services, you have an acceptance. Then generally you have always an anamnesis. It's very important, the anamnesis phase, considering the kind of patient and the status of the patient. We spoke about glucose, that is sugar, and that have to be injected to the patient. So, for example, just an example, the people who have diabetes to be checked, otherwise it can be dangerous. And so this is just an example of the importance of anamnesis. The second example I would give you is just about justification principle. The nuclear medicine is always for the I would say just to permit to have images, the patient have to be exposed to radiation, and this can be dangerous for the patient. So this danger have to be justified, considering the benefits that the patient can have from a diagnosis. Then the patient, after the anamnesis, goes inside the PET-CT center, and where it can be injected. And as we already listened to, the patient has a phase of biodistribution, in which, in general, the tracer can go inside the dynamic of metabolism of the patient. Can be from for example, 45 to 60 minutes long. Then the patient go to the PET-CT scanner and make the diagnostic exam. The physician, in general, the physician obviously are always in the hot area, just to check and control the right protocol, but there is always an area that is in a cold area, that is placed in a cold area for diagnostic imaging analysis and for reporting, that had to be in the cold area. I would underline a principle in the layout, that is the one-way patient path is very important. The principle, we can say that the patient have never to step back from the entrance to the exit of the department. In this way, you are right. You are for sure the distribution of each space as coherence with the kind of action that you have to do on the patient, and above all, from the considering the safety of both patient and operator is optimized. You never, in general, the patient should not cross or the path of other patient, because the exposure of another patient to the first one is an exposure that shouldn't be justified. With the same principle, the operator maximize their safety. Okay, here just another example, a little more complex, considering a department with both PET-CT and SPECT-CT. So two modalities, different modalities in nuclear medicine. A little more complex, again, we have cold area, hot area, but for other complexity in systems and considering the facility, for example, for the hot bathroom is an example of the motivation. You have to separate area with different modalities that are based on different kind of isotopes. Okay, so generally in the PET-CT area, you have fluorine and other isotopes. In the SPECT-CT area, you have the technetium compounds. So you have to separate them. Again, you have a one-way patient path for the SPECT-CT and the other for the PET-CT. Okay, so I think we can launch the first poll that I hope is clear. I think that is clear that both was the right the right answer to the question. You're right, right? And as I did for the layout for the, I would say, diagnostic floor, this is the radiopharma production floor. I want to show you just a standard layout. Here in the lower part on the right, you see the cyclotron that is inside a bunker, a vault. And it's very important to understand that in this kind of layout, each room has is dedicated to some task, very specific task. The action on the pharmaceutical can be done inside controlled area, rooms, and devices in some case. For those who are more confident with and more that know more the standard of the operating room, on the right part of this slide, you can see the layout, but also the classification of the operating room. I would consider the standard, the international safety standards 14644 for the classification of the operating room. Just an example, the ISO class 3 is for the surgical procedures that had to be done with the maximum level of asepsis. The transplant had to be done in ISO class 3. In radio pharma, we have the same kind of classification from A to D, and the most critical action on the compound, on the product, had to be done in A, and other. You have cell for typically there's dedicated devices classified in A, and other room that contain this kind of cell can be in B. And going to not classified area, you go through C rooms or D rooms. Okay, so from the radiopharmacy to not classified rooms, you go from A to D not classified areas. Generally, the workflow is typically you have a delivery from the cyclotron to the radiopharmacy. In the radiopharmacy, you have the synthesis, that is the, I would say, just the link between the isotope and the pharmaceutical. That is a series of chemical reactions. Then typically you have to make the quality check, and after the quality check you can deliver. And delivering, you just make the availability of the dose for the final patient. Okay, just another point on this slide. We spoke about asepsis. The gradient of pressure in asepsis, for asepsis, should be like that. So in the radiopharmacy, you would have the maximum pressure related to the rooms that are near the radiopharmacy. But you have also a problem of radioprotection. And thinking about radioprotection, you would have the opposite one. So typically in the layout, and particularly in design, the HVAC system, you solve this kind of problem with particular aspect and technicalities that are related to little rooms that can be sort of boundary of the of control of the pressure. Okay. It's very important to consider that are different the radiopharmacy for industry and for hospital. The industry as a are in a commercial setting, so the final goal is to put a product in the market and to sell it. And on the contrary, the hospital radiopharmacy as in a clinical setting, above all, is not related to GMP standard that are very strict standards, and are not in permission by generally by investigational authority, but only by ethic committee. Okay. Here you have, I think, the core of this presentation. There are the flow of the patient flow and the radio pharma production flow. I want to give the evidence of the injection phase. That is the coincidence, the question of coincidence. When a patient has had to do this kind of diagnostics, always have a prescription of a tracer and an activity, a dose. And when the nuclear medicine physician give you those, generally give also the, you always have to fix calibration time. Okay, you have always to consider a calibration time. So at that time, you should have the patient prepared for the injection, and at the same time you have to have the dose dedicated to your patient at that time ready for the injection. So and this is very important because you always have a decay. So there is always a timing issue when you have to deal with nuclear medicine exam. Just 6 point, very important point in the flow. It's very important to schedule and reschedule very quickly. because of the decay of the tracers. So it's very important to have tools that are useful for the scheduler. Again, we saw the path of the patient that is quite complex path. So it's very important the communication with patient during the phase of acceptance, analysis, preparation. Yeah, it's very important to have data on the same RIS, on the same radiological information system. This is very important by my point of view. Above all, if you want an automatic scheduling, because it's very important to know how much you can produce or how much has been produced to know if the rest of the patient that you have in list can be for them can be done the exam. Again, we spoke about safety. It's very important to have a dispensing system that are connected with DICOM workflow class, like a tomograph, and like the normal connection of a tomograph with RIS, just to be sure about the anagraph data of the patient, to be sure that the patient is the one that will do the diagnosis in the tomograph, and the same one that for whom you have produced the dose. So it's very important to have this kind of connection for the safety of patient. It's very important to have the timing of injection. That is the real time you have injected the patient. And I would underline also some, I would say, innovative way of thinking about scheduling. I called it that, like parametric scheduling, but we will speak about it after this question too. This is a real tool. This is in Italian because I would show you a real tool. This is an attachment of a protocol. How can we set a protocol? Obviously, diagnostic protocol. Always you have to indicate with a code the protocol. It's important to have an acquisition in the acquisition workstation, the same protocol that is clarified for the technician, which is the protocol related to the one that you are that are the base of the diagnostic for the patient. So the technician have to know what have to be launched on the acquisition workstation, and that is related to the protocol. It's important to know the dose, radioactive dose, so how we quantify the dose. There are different methods, and the general workflow. Again, we have biodistribution, acquisition, reconstruction, and the time. We consider always the time to close the exam to the patient for a total time of the slot. Okay. We spoke about parametric scheduling. Just an insight about it. We always have many protocols and different timing for each patient, for acceptance, analysis, patient preparation, injection, distribution, and diagnostic acquisition. A new way to use this timing data is to stop using standard slot, static slot, considering the duration, but dynamic slot, considering the data that you can have from your own activity, and considering so the variability and the average time that are the basics of the scheduling that is working on your risk. So it's a new way of to consider data as a sort of quality for patient. Okay, just few words considering productivity. These are data from European Union. Sorry, I didn't find any updated data on all over the world. Here, very useful, the number of PET-CT scanner per tomograph. As you can see, I would say a high level, high productivity level for each tomograph is 3,000 or more patient per tomograph per year. This is a per year data. Typically, from 2,000 to 3,000 is middle value. Under 100 is there is a low level of productivity. Just to give you some insight about productivity of this kind of PET-CT center. Here is just give you an insight about next step. Just a few words. From my point of view, what are the four main line of general development in PET-CT? For sure, new tracers, for sure, new targets. This is very recent in imaging of bacteria by PET-CT. The devices, the long axial field devices are very interesting, like 1 meter in axial FOV. That is really a lot, and 2 meter for 1 meter for from one supplier, 2 meter for another one, and an elaboration of data for the quality of images. Thank you so much for the invitation again.
We thank you so much, Giulio, for this third excellent presentation in today's webinar. Thank you for introducing us to the complex picture and giving us the complex picture of not only of the PET itself, but of the whole PET installation with the generator or the cyclotron and the radiopharmacy department that should be included. And this is that makes this diagnostic imaging tool quite difficult to implement, especially in cases that there is no much experience and there is not it is not well supported by medical physicists as well. So I would like now to open the question and answer session and see how well we can respond to the questions of the audience. And I would like also to thank the audience for their participation in the polls and in the questions and answers session. So, Kaliroy, I think that you should take the lead now. I have not too much experience on how to moderate this part of the session.
We could address some of the questions that are on the Q&A gathered so far. So,
okay, then we have to go from the beginning.
We can select a subject like clinical question, safety questions, and process questions, and that would give all the panelists opportunity. For example, there were questions about what is the, that's maybe for Dr. D'Souza, what might be the time requirement to wait between injection for diagnostic purpose on the same patient?
So, related to this question, it depends on the radio tracer that you are applying, because some tracers have a short half-life, and then you can have another scan hours or 1 day after the first injection. And for others, we have a higher time between the one scan and another.
Thank you. Thank you. If I may jump, to Claire, a question was posted on the containment issue, and that is specifically for bathrooms used in what Iketi referred to as the hot area. You're on mute.
So generally have a radioactive toilet. So the toilet, well, the hot toilet that the patients use. So yes, the flooring would be generally continuous with the wall, again, so easy to decontaminate if there was any contamination present. That's the sort of, I don't know if that's answered the question, but that's the sort of thing.
I think the questionnaire, the person who posed the question was concerned about impact on the community from discharging maybe radioactive material.
Oh, right, I see. So so in the UK we have to apply to the Environment Agency, who allow us to dispose of radioactive material down the drains and into the sewers. And to do that, we have to do something called a radiological impact assessment. So we have to estimate or calculate the amount of radioactivity that will go into the sewage system, and then work out the potential impact on radiation dose to different members, different people who could come in contact with it along the line. For example, a sewage worker, somebody working on the drains, that sort of thing. So, but in general speaking, in terms of PET tracers, they're generally shorter lived, and there's quite a high dilution factor when it goes into the sewage system. So compared to other nuclear medicine studies, therapies, for example, with I-131, where it's a much longer lived radionuclide, it's a PET fluorine 18 anyway, it's very short lived in comparison to the time it takes to get to the sewage system. So sewage treatment works. So it's of low impact into the environment.
Okay, thank you. As you all can see, the panelists are so expert and the audience is so dire to have better understanding. Perry Boris is a medical physicist, asked to see if we can show what the right answers are to the polling questions. But while maybe we try to provide that, I would like to jump into the presentation Iketi you made, with statistics and numerical analysis of numbers of devices and population and so on. And the question came up for you, if you can identify somehow financial question, the cost of providing all the installation of the hot, cold, scintillations, and cyclotron work versus the cost of maintaining it?
Yeah, generally is cost-intensive project for sure. Obviously, you have to consider, I would say, capital cost and running costs. It's very important to consider differences between these two. In the capital cost, for sure, the highest. It depends. If we are speaking about a new department, for sure, the building of a new department is very, very expensive, considering radio protection, considering the design first of all, the design and the building of there are a lot of particular detail that have to be considered. All the things that are inside radio pharmacy are very customized and related to the production. In some case, to the isotope that I want to produce. An example is the metal target is an example, just an example. The metal target isotope are the newest and have a strong impact on the capital part of the project. Considering the current cost, for sure, you have obviously in the capital cost the tomograph. If you choose a long bore tomograph, it's a very, very high level tomograph. The cost can be impressive. Otherwise, the cost of a PET CT in euros nowadays can be on average really like 2 million euros. Okay, and considering the cost of maintenance, generally we consider always the cost for the scanner and never the cost for radiopharmacy. It's very important to consider the cost for radiopharmacy because can be quite expensive because of the activity to have a safe device. You have always filtration, but with particular filters considering radioactive materials, calibration of detectors, in general, the maintenance of the radiopharmacy is quite high cost, yeah, and training, and also
yeah.
For the staff is very important because the innovation in this kind of branch is faster and faster, and it's important to be updated to have the possibility to exploit the devices that you have.
Great, thank you. Very complex system and tremendous financial burden, but the clinical benefits are perhaps worth all of it. There are many more questions. I will hand it back to the moderator, Professor Palekrakis, and to Kaliroy, and just thank this awesome faculty, great presentation. I really learned a lot myself from it. And thank you, GCEA, for providing the live captions in multiple language today. Back to you, Nicholas.
Thank you very much, Yadin. And thank GCEA for this series of webinars. Thank Professor Khalil Thank you very much, Khalil. But first of all, I would like to thank the three speakers. We enjoy very much your presentation. We learn a lot, and I hope that not only the 2,000 participants in this webinar that follow this, more than 2,050 in real time, a lot of hundreds or thousands will see it later on. So thanks again to all the participants for participating in this webinar, and thanks again to the speakers that they provide us so beautiful presentation on this very complex subject in such a short time. Thank you again all.
Well, I just want to add just a few words. I would like to thank you
Please,
all of you
please, Khalil.
for accepting the invitation. Really, it's not easy to find experts that have the time to come here and offer such teaching, I would say. Thank you very much for all of you. And don't forget that, as Khalil put in the screen, every recording, all the recordings will be in the site of the GCEA. So thank you all. Have a good evening, have a good day, and good night. Thank you very much. Bye.
Thank you all. Bye-bye.
Thank you very much. Bye-bye. See you soon.
See you soon.
Very much. Bye bye.